Hello, the topic for this presentation is Analyzing the Impact of Demonetization on Digital Payments in India. The topics that will be covered are Introduction, Research Question and Objectives, Methodology used, a demo of the implementation and a discussion of the results, and finally the conclusion. Introduction. Demonetization is defined as the act of removing the legal status of a currency. In India, the recent demonetization was implemented by the government in November 2016 and the currency notes of Indian rupee 500 and 1000 were demonetized. These notes constituted over 86% of the currency in circulation in the country at the time. Given the huge cash dependence in India, the demonetization came as a great shock to the citizens as well as businesses. The ban on existing notes came into effect immediately and the new notes were not available for a considerable time. This led to people shifting to alternative modes of payment. Previous works in this research area show that demonetization caused a huge increase in the usage of digital payments. This research aims to determine the immediate as well as medium to long-term impact of demonetization on digital payments in India. The research question is as follows. Has there been a significant and long-lasting impact of demonetization on the growth of digital payment systems in India? The objectives of this research are to analyze the impact of demonetization on digital payments, to analyze if there was a significant growth in the usage of digital payment platforms as a result of demonetization, and to determine whether the increase in digital payments was a temporary effect caused by cash crunch during demonetization or has it been persistent post demonetization. The methodology used in the research includes 5 main steps. First is data selection and preparation. Next is exploratory data analysis. Next, model estimation, followed by diagnostic tests and forecasting and interpreting results. The first step includes data collection and pre-processing. The data used for this research includes monthly volume and value of financial transactions from various payment systems, and it is obtained from the Reserve Bank of India website. Of these, only the digital payment systems like real-time gross settlement, retail electronic clearing, debit and credit card usage at POS, mobile wallets and mobile banking are considered for this study. The transaction volume and value from individual systems is converted to percentage terms by dividing by the total volume and value respectively. This is used for exploratory data analysis. The total volume and value of digital transactions is calculated by summing up the individual mode-wise volume and values. This is also converted to percentage terms by dividing by the total volume and value of transactions. This data of total digital volume and value will be used for further analysis instead of the individual payment system data. Other activities like changing date to the required format, type conversion of numeric data, and ordering by date are done in this step. The next step is exploratory data analysis. This includes visualizing the data from individual payment systems over the period of study and in percentage terms as well. Step 3 includes model estimation. The first model estimated is the segmented regression model, and this is used for preliminary analysis of the data. This model fits segmented linear regression lines to the data based on the intervention point specified and detects the change in level and trend in the different segments. The next two models are used for time series analysis. Therefore, the data is converted to time series and split into train and test sets. The next model used is dynamic regression model or regression with ARIMA errors. Here, an external regressor variable is used while estimating an ARIMA model on the train series. The external regressor is estimated in two ways. First, by using breakpoint analysis to determine if there are any significant structural breaks in the time series, and using the breakpoint index to create a level shift regressor with value 0 before the breakpoint and 1 after it. The second way is to detect level shift and additive outliers in the data and use those as external regressors. The next model used is the ARIMA transfer function model. Here, various transfer functions like pulse function and step function are estimated and used as covariates. The lagged effects of covariates are also included in model estimation. After model estimation, the next important step is performing diagnostic checks on the estimated models. The most important test for ARIMA models is that there should not be any significant autocorrelation present in the residuals of the model. This is checked using the autocorrelation plots of the model residuals. Another important test is to check that the residuals are white noise and are normally distributed. This is performed by using the Leung-Box test. A high p-value of this test indicates that the residuals are white noise and the model estimation is considered to be good. The diagnostic tests are performed for all models, and if any model fails these tests, then the ARIMA order is changed and the model is tested again. The final step of the analysis is forecasting and interpreting the results of the models. When multiple models are estimated, the best model is selected based on the least values of information criteria like AIC, AICC, and BIC. The models that pass diagnostic tests are used to forecast for the test period. The forecast errors are computed using measures like mean absolute error, root mean squared error, mean absolute percentage error, and mean absolute scaled error. The model having lowest errors is selected as the best model. The coefficients of the ARIMA transfer function model are used to determine the magnitude of change in the mean function of the time series. The implementation and demo of the code is presented in the next part. This R file contains the code developed for this research project. The first step is to install the required packages and load the required libraries. The data is available as CSV file and is loaded in R. Next, the unwanted rows are removed. The pre-processing activities like changing date format, ordering by date, and converting value into numeric format are done. This data contains transactions from all payment systems, including digital and non-digital, as the focus of this research is to study the impact of demonetization on digital payments. Only the digital payments are considered. This is done using the following code. Next, the individual mode-wise transactions are separated into different datasets to plot and visualize their trend. For the card usage data, the credit card and debit card usage data is available in separate columns. It is added together and visualized as total card usage at POS. The mode-wise transaction volume is visualized in a single plot. The dotted line denotes the demonetization time. Similarly, the mode-wise transaction value is also visualized. Next, the individual payment mode transaction volume and value are converted to percentage terms by dividing by the total volume and value respectively. The volume in each payment mode as percentage of total is visualized by this plot. Similarly, the value in percentage terms is also visualized. Next, the total of digital transaction volume and value is calculated by adding the individual volume and value and converted to percentage terms. These data are plotted. The next part shows model estimation and testing. The first approach used is segmented regression. In this, three variables are added to the data frame. First denotes the time encoding, which starts with 1 and increases successively until the last time point. Second is the intervention effect, coded as 0 before and 1 after the intervention date, which is November 2016. The third is denotes the time after intervention. It is coded as 0 before intervention and increases successively starting with 1 after intervention. The autocorrelation in data is accounted for by using the core ARMA function in the correlation parameter of the GLS function. The summary of the model shows the coefficients. The QQ plot shows that the residuals do not follow a normal distribution. The ACF plot shows that the residuals show significant autocorrelation. The model fit is plotted. The fitted lines show a clear difference in the level and slope of the data before and after demonetization. The coefficient estimates indicate a growth of about 10% in the level and 0.57% in the slope. Similar estimation is done for the digital value data. The fitted lines show that the level of the data decreased slightly after demonetization. The coefficient estimates show that the level decreased by about 1.6% and the slope decreased by about 0.07% after demonetization. The next model estimated is the dynamic regression model. For this, the data is converted to time series. The stationarity of the time series data is checked using ADF and KPSS tests. Both these tests indicate that the data is not stationary. The index function is used to find the number of differences used to make the data stationary. On taking the first difference, it is found that the data becomes stationary. This indicates that the order of differencing should be 1. Auto.arima function is used to determine the order of arima, thus the raw data is used in the analysis. The data is decomposed and seasonality is removed from it. Next, the data is split into training and test sets by using the date as November 2018. The last 12 months are used for testing purpose. In the dynamic regression model, the external variables are used along with the ARIMA model. The external regressors can be determined in two ways. First, structural breakpoints are estimated by using the breakpoints function. A breakpoint is detected at November 2016. The data is plotted with breakpoints. The index of this breakpoint is used to create a numeric vector having values 0 before the index and 1 after the index. This numeric vector is used as the xreg parameter in auto.arima function. In the auto.arima function, the stepwise parameter is set to false in order to prevent skipping the ARMA orders, and the approximation equal to false is used to prevent the function from approximating the value of information criteria while selecting the best model. And the method indicates that the maximum likelihood estimate is used for model estimation. Diagnostic checks are performed by plotting the residuals from the model. The check residuals function is used. The volume box p-value indicates that the residuals are white noise, and the ACF of the residual shows that there is no significant autocorrelation present in the residuals of the model. The forecast method is used to forecast the values for the test period. The forecasted values are plotted and the forecast accuracy is calculated. This shows the error measures. Other models are estimated by changing the ARIMA order. The values are forecasted and plotted. Only those models are used which pass the diagnostic tests. The information criteria values are compared, and the forecast accuracies are also compared. The model having the least value of error measures is selected as the best model. Similar process is followed for the digital value data. Let's convert to time series, perform the stationarity tests, and adjust for seasonality, split the data into training and testing, check for structural breakpoints, use the breakpoint index to create a numeric vector, use that numeric vector as external regressor in the AutoData function, perform diagnostic tests, forecast, calculate accuracy, and try different orders of ARIMA. The information criteria values are compared to find the best model having the least values, and the forecast errors are compared to find the model having the least error measures. The second method used to determine the external regressors is detecting the level shift and additive outliers and using those as XREG values. The TSO function from the TS outliers package is used for this purpose. The outliers detected in the digital volume time series data are as seen here. The effect of these outliers at each point in the time series is detected. This is done for both level shift and additive outliers. This is then used to create a matrix and passed to the XREG parameter in the auto.arima function. The estimated ARIMA model is this. The diagnostic checks are performed on this model. Here the Lumebox p-value is very small. Also the ACF plot shows significant autocorrelation at multiple lags. Therefore, model order is changed The new estimated model can be seen here. The residuals of this model are white noise. In order to forecast the values using this model, the future value of x reg needs to be determined. For level shift, the future values will be 1, and for additive outliers, the future values will be 0. Thus, a matrix is created using these values and used in the x reg parameter of the forecast function. The forecast and actual values are plotted, and the forecast errors are calculated. The order of ARIMA is further changed and tested. The AIC value is calculated and compared to find the best model, and the forecast accuracy is also compared to find the model with the least error measures. Similarly, outliers are detected in the digital value time series and used for modeling in the auto.arima function. The outliers detected in the digital value data can be seen here. The outlier effect at each time point in the digital value series is calculated, and this is used as xreg in the auto.arima function. Diagnostic tests are performed on the detected model, and the values are forecast in a similar way. Other models are estimated and tested by changing the ARIMA orders. The forecast errors are calculated and compared to find the best model. The next model used is ARIMA intervention model using transfer functions. For this, the ARIMA order is detected by using auto-ARIMA function on the pre-intervention series. The best model detected by auto-ARIMA function is then used for the train series by using the ARIMA X function. The covariates are estimated here. The covariates can be created as either pulse function or step functions. The pulse function indicates a temporary change and step function represents a permanent change. This model shows a pulse function. X parameter contains a data frame, which is a pulse indicator variable whose value is 1 only at the intervention time and 0 otherwise. The transfer parameter takes a list of AR and MA orders. In this model, the AR and MA values are 0. The residuals of the model are checked. The ACF plot looks good. The next model is estimated using a step function. Here the value of the covariates is 1 after the intervention and 0 before it. The residuals indicate that the model is good. The next function is estimated as a pulse function with lagged effects. So the AR is specified as 1. Another model with step function is estimated using AR equal to 1. Next, estimate a pulse function plus step function with AR1. In this case, the covariate includes two columns. One indicates the pulse function and the other is the step function. For the pulse function, the AR and MA values are 0, and for the step function, the AR is specified as 1. The residuals of all models show that the estimates are good. The best model is selected based on the least value of AIC. So the best model here is step function with AR1. This model is used to forecast. To determine the effect of the covariates, the filter function is used. Plus 12 here indicates that the effect of covariates is determined for the future 12 steps. As the TSA function does not provide any predict or forecast function, the estimate is used in a REMA function and passed in the XREG, and the order used is the same as the one determined previously. These forecasts are used to plot. Next, the impact of demonetization is calculated. This plot shows that the impact increased gradually and then remain constant. The magnitude can be calculated. The model accuracy is calculated. Finally, the accuracy of all different types of models is compared. Similar transfer function analysis is performed for digital value data by estimating the pulse function, step function, pulse with AR, and step with AR. The AIC of all different models estimated is compared to find the best model. The impact is visualized and the accuracy is calculated. Finally, the accuracy of all different types of models is compared. Shows that the regression with ARIMA errors performed the best. Discussion. The dynamic regression model coefficients show that the impact of external regressors was significant on the digital transaction volume data, but for the digital transaction value data, the external regressor coefficients were not very significant. This suggests that the impact of demonetization was significant on the volume data, but not on value data. The coefficients of transfer function models show that there was an instantaneous increase in the digital transaction volume by 10.17%, but in case of digital transaction value, the change indicates a drop by 1.85%. The results show that the impact on both the data were permanent. Conclusion. This research shows that demonetization caused a sudden increase by over 10% in the digital transaction volume in November 2016. This change kept increasing gradually until November 2017, when it reached about 15% and has remained at that point thereafter. The impact of demonetization on the digital transaction value was a sudden drop of 1.85% in November 2016, which has remained constant since then. Thus, the findings of this research show that while demonetization led to an increase in the digital transaction numbers, it has not caused an extreme shift in the payment behavior of the Indian people.